Hello out there. Welcome to the recording of the talk Learning Formulas in Finite Variable Logics, which I presented at POPL 2022. My name is Paul Krogmeier. This is some joint work with Madhu Parthasarathi at Illinois Urbana-Champaign. All right, here we looked at exact learning problems in logic. So we're looking at problems where you're given some examples and you want to learn a concept. But here the concept is logical. So you have a search space, a hypothesis space of logical formulas. In another case, it's logical terms. And your examples are first order structures. So you can take this for a mental image. Maybe the structures are just finite graphs, and you're trying to classify them with a formula in some logic. So two reasons to look at this. The first is that we want to understand the outputs of algorithms. And one natural way to get that is to search in a space where the things you're searching for have some clear semantics. So logic is a good place for this. And second, there's a lot of first order structure in our data. As I have some examples here, program states, relationships between variables and programs before and after executing code, different kinds of data types, algebraic data types, built up with functions, broken down with other functions. And relational databases are first order structures in a relational signature. And then images, objects and relationships in images can be modeled as structures. So there's this abundance of structure in our data, and we want to learn something from it. Okay, let's see three examples here. Here's the first one. So suppose you're given these finite graphs. So there's four. The two on the left are labeled positive. The two on the right are labeled negative. And your goal is to find a way to separate them with some logical concept. So in this case, let's suppose you're trying to find a first order logic sentence that is true on the positive structures and false on the negative structures. So you can pick a sentence from this grammar. So this is just usual first order logic in the appropriate signature. So it has an edge relation E and then these two constants S and T. Now, if you know something about first order logic on finite structures, you may know that you can characterize any finite structure up to isomorphism. What that means is you could overfit to the positives if you wanted to. You could pick a sentence which says everything that you can possibly say in first order logic about the positive structures. So we want to avoid that, and one way to do that is to suppose you're given, in addition to these structures, you get a grammar that specifies a syntactic fragment that you have to pick your separating sentence from. Okay, so there's one restriction. Now I've changed the grammar so that you can't use arbitrary combinations of negation and disjunction, and instead you have to use an implication. All right, so one solution then could be this. This just says nodes adjacent to S can get to T in two edges. So is that true? Okay, first positive structure on the left. Here are two nodes adjacent to S, and they each reach T in two edges. Okay, second positive structure. That's vacuously true because there are no nodes adjacent to S. Leftmost negative. We can take this node, which is adjacent to S, but needs more than two edges to get to T. And for the last negative structure, we can take either of these two nodes, which are adjacent to S, but need three edges to get to T. Okay, so this is just a basic example for the kind of problem we're thinking about here. Here's a slightly more complicated one. So this is the same problem, labeled structures that you want to separate by finding some formula in logic. So you stare for a little bit, you see, okay, these are directed graphs now, and I see the two on the left, the positives, each have a cycle, and every node can reach the cycle. Okay, so maybe that's your concept. All nodes can reach a cycle, but you may know also that in first order logic you can't express cycles, you can't express reachability. So if you want that for your concept, you need to assume a richer logic. And one such logic is a first order logic with recursive definitions. And then one solution could look like this. So this is kind of just a stylized syntax for FO with recursive definitions. So this sentence just says, let me define a binary relation reach that holds between two nodes x and y in the graph if x can reach y in some finite number of edges. And then having defined reach, it just says, for all x, there exists a y such that x reaches y and y reaches itself. Okay, so these are just two examples for what we call the separation problem. You get labeled structures and a grammar, and you're looking for a sentence which separates them. And you can ask this question in a variety of different logics with varying expressive power. Here's a slightly different problem. So again, we're going to have structures as examples, but now we're trying to synthesize a term in a logic, so term synthesis. So let's model a list domain. So let's suppose the elements of our structure are lists up to length 3, in addition to some elements from some ordered domain. Okay, and our signature is just going to model some usual list operations. So cons, head, and tail have their intended meaning. They're just first order functions. And then we have a constant nil for the empty list. Okay, so one slice of this structure looks like this. It's got the ordered elements here on the bottom, and then an empty list nil. And you can build lists with cons and break them down with head and tail. Okay, and let's take all the lists up to length 3, say. Okay, so here's a structure. Let's also suppose that it interprets some input constants and an output constant. So let's say there are two input constants which are interpreted as the lists A4 and A2, A3, and then the output constant is A2, A3, A4. So now given that structure, which sort of encodes an input-output example over lists, you want to synthesize a term t so that t is equal to out in the structure. All right, so one solution could be this. It defines the merge function on two sorted lists. So this is a spruced up version of first order logic terms where you can define terms recursively, and there's an if then else term. But then having defined merge in the usual way, it applies it to the inputs. Okay, so we saw examples for separation, for synthesizing terms. Let me just state the problems formally now. Okay, the separation problem, given a logic L and these two sets of structures, one positive, one negative, and a grammar G, synthesize a sentence from the grammar that is true in each positive structure and false in each negative structure, or say unrealizable. So we're hoping for decision procedures. We looked also at a query synthesis problem. So this is given a logic L, and now the structures don't have labels, but they come with answer sets. So each structure comes with this answer set, which is a set of tuples over the domain of the structure that should make the query that you want to synthesize true. And then again, given a grammar G, now you're synthesizing a formula phi with some free variables from the grammar so that the set of tuples from the domain, this A bar, that make the formula phi true is precisely this given answer set. Okay, and then finally, the term synthesis problem corresponding to that list example. You get a logic L and a set of structures, each one interpreting some input constants and an output constant, just modeling input-output examples, and a grammar G. Synthesize a term T from the grammar so that in each structure T is equal to out. Okay. The contribution of this work is really a set of decision procedures for all three of those problems in finite variable logics. What is a finite variable logic? It's what it sounds like. It's a logic where formulas and terms, no matter how large, can only use variables from a fixed finite set. This does not mean, though, that they can only have finitely many occurrences of variables, because in terms, you can shadow the bindings of variables can be shadowed, and in formulas, they can be requantified. Okay, so it turns out that this is an infinite search space, even with finitely many variables. So if you take just first order logic with 3 variables, you can define a binary relation, path I, one relation for every number I, that holds between two nodes in a graph, x and y, if there's a path of length I from x to y. So, okay, so there's a path of length 1 if there's an edge between two nodes. There's a path of length I plus 1 if there's an edge from x to some z, and a path of length I from z to y. Okay, so the thing to notice is just that this variable here, x, is being re-quantified and then set equal to z and then being reused in the definition of path I. So the point is you've got these infinitely many inequivalent formulas being defined with only 3 variables. Okay, so we do have decision procedures for these problems, searching over an infinite space of formulas and terms. So the 3 problems were separator synthesis, query synthesis, and term synthesis. So they're each decidable for first order logic with k variables, which we call FOK, for FOK with nested definitions like the reach definition, for FOK with recursively defined relations like reach and recursively defined functions, and also for finite variable versions of higher order logics. So here's just some complexity. The first order versions of all 3 problems are x time complete. So here are some of the parameters here. M is the number of structures, exponential in the number of structures, n is the size of structures, so exponential in the size, and k is the number of variables, so doubly exponential in variables. And we can also handle languages with mutual recursion and some kinds of background knowledge using the grammar. So this lets us synthesize, for example, data log programs from examples and handle some problems from inductive logic programming. And like all the decision procedures I'm going to talk about here, they're sort of uniform in the sense that they use the same main building block. They involve tree automata. So now I'm going to focus on what that building block is. Okay, the idea is we want to define tree automata that evaluate syntax trees. So from now on, when I'm talking about formulas and terms, I'm thinking of syntax trees. And our goal is going to be defining an automaton which reads trees and evaluates the semantics of a given logic against a fixed background structure. So these are automata that walk down a tree and change their state as they go and accept or reject at the end. So let me just situate that in the context of finding a decision procedure for this separation problem. So remember, this is, you get a logic and these 2 sets of structures, positive structures and negative structures, and a grammar, and you want to find a sentence in the grammar that's true on the positives and false on the negatives. Okay, so first step, for each positive structure P, we want to define an automaton AP whose language is the sentences that are true in the structure P. Okay, I'm going to focus on that step. So let's just assume we have that. Assuming we do, it's straightforward then to, for each negative structure, define an automaton AN so that the sentences in the language of that automaton are the sentences not true in N. And then assuming this grammar G is a tree grammar, we can define a tree automaton AG that accepts sentences conforming to the grammar. And then we can take a product automaton of all these automata from above, and semantically its language is the intersection of the languages of its constituents. So that's just the sentences from the grammar that are true on positives and false on negatives. And then finally, we can check emptiness of this product automaton, and if not empty, we can construct a formula or a term. Okay, so let's focus on point 1 here. We have a given structure, and we want to define an automaton that accepts sentences that are true in that structure. Okay, so let's focus on the logic FOK, first order logic from using a set of k variables, so from a set V here. And let's fix a finite structure M, and M has some signature which won't be important, okay? And now we want to define this automaton A that accepts a sentence phi from FOK precisely when phi is true in M. And now here is where the finite variable restriction plays a role. So we said that there are finitely many variables, V, there's K variables. We said that the structure M is finite, and therefore there are only finitely many assignments to variables. Okay, so we're going to take the assignments, gamma, as the states of the automaton. And what we're really after is we want the language of the automaton in state gamma to be the formulas phi that might have free variables that are true in M with the assignment gamma. Okay, so I said we want to define an automaton. What kind of things can we say? So we're defining a tree automaton. So first and foremost, a tree automaton reads labeled trees. In our case, they're syntax trees. Maybe it's a syntax tree for a formula or a term. And the idea is when an automaton like this is reading an input tree, it's at a particular node in the tree in some state. And it needs to decide how to send updated copies of itself in new states in the subtrees, the subformulas or the subterms. Okay, and the idea is that this tree automaton will accept its input tree if all of the children copies accept. Okay, so the kinds of choices it can make about how to send updated copies in different states into the children depends on this transition function. Okay, now in the case of alternating tree automata, the transitions can be basically propositional formulas, which kind of describe all the different ways that the automaton could descend into its children in different states. So for example, you could say something like, okay, the automaton needs to either, that's this or here, either go into the left child in state Q or into the left and the right child both in state Q prime. Okay, the main idea is just that alternation lets us very neatly and concisely express the semantics of first order logic. Okay, so I'm just going to show some kind of sketches of what the transitions look like. So remember, M is this fixed structure and gamma is a particular variable assignment. Okay, so here on the left, the automaton is in a state gamma, an assignment reading disjunction at the particular node it's at. Okay, and these dashed arrows are just saying the automaton gets a choice. It can either descend into the left subformula and succeed in the same state gamma, or go to the right subformula in gamma and succeed. And then conjunction is similar, except we've got a solid line, and this is just saying it needs to succeed from both subformulas in gamma. Okay, here are two base cases. In gamma, and reading Rxy, so this is just an atomic formula, relation symbol R, the automaton just accepts as long as Rxy is true in M with assignment gamma. And similarly, it'll reject if that's not the case, okay, if Rxy is false. So for quantification, this looks like disjunction and conjunction. So in state gamma, reading exists X, the automaton goes into the subformula and it gets a big choice. So it can succeed from any one of these updated states, gamma I. So gamma I is the assignment gamma where X is updated to map to the ith element of the domain of M. And then universal quantification looks similar, except it needs to succeed from all updated assignments. Okay. And then finally, reading a negation symbol in state gamma, the automaton goes into the subformula and marks its current state, this gamma tilde. And that'll just let it remember that it needs to check that the tree it's reading is false instead of true. And it can do that by treating the symbols as their duals, essentially. Okay, how do we read recursive definitions? So back to the reach example from before, where we said all nodes can reach a cycle. Okay, how do we read this? Well, first, what is the semantics of reach? So it's a least fixed point semantics. What does that mean? If you take the formula to the right of the equals sign here, the defining formula, you can treat it as a function on relations, which turns out to be a monotone function, and so it has a least fixed point. And we take the meaning of reach to be that least fixed point. So then when the automaton is reading something like all nodes can reach a cycle, it needs to check membership in this relation reach. And it does that by computing the least fixed point. So the idea here is we move from alternating tree automata to two-way alternating tree automata. And so these are automata that can walk up and down on their input tree many times. So this will allow us to define an automaton that computes the least fixed point in order to check membership. So here's an animation of that happening. So here I've got the syntax tree for the all nodes can reach a cycle sentence. On the left here is the part that says all nodes can reach a cycle, and the right is the definition of reach, okay, which is recursive because it uses the symbol in the definition. All right, so on top we have this 4-element structure ABCD with a directed path from A to D. And now let's assume the automaton is in the lower left corner reading reach xy in a state that maps x to A and y to D. So it needs to check that AD is in the least fixed point. So how does it do it? It walks up to the top of the tree and finds the definition for reach, and it's going to now go down into the definition and read it many times, kind of computing the least fixed point as it goes. So in the first iteration, it ends up at the bottom, and it needs to check, okay, is there an edge from A to B, and does B reach D? So yes, there's an edge from A to B, and to check B reaches D, it walks back up to the top of the tree again, and the whole thing repeats. Okay, so it walks down, and the same thing happens, except now it needs to say, okay, yes, there is an edge from B to C, and let me check that C reaches D. So again, it walks back up to the top, and this time it descends into the base case, no more recursion. Yes, there's an edge from C to D. So this tree gets accepted starting in the state that we started in. Okay. So the takeaway from all this is we're kind of using tree automata as a sort of programming language for designing decision procedures for synthesis in logics. And two main ideas. The first was alternation was convenient for expressing the semantics of quantification, and two-way automata were convenient for recursion. And this finite variables restriction is what enabled us to sort of precisely evaluate the semantics of these logics using automata. Okay, to conclude, we looked at exact learning problems in logic, in particular in these finite variable logics. We looked at 3 problems for synthesizing separators, queries, and terms. And we have decision procedures for synthesizing formulas and terms in logics with nested definitions, recursion, and mutual recursion. And all of the decision procedures essentially rely on the same component, and that is a tree automaton which reads syntax trees and evaluates the semantics of the logic against a fixed background structure. Okay, 2 things I think are interesting for future work. The first is, are there algorithms that run efficiently in the number of structures? So you saw that the decision procedure for separation involved this big product automaton, so 1 automaton per example structure. And that made the complexity exponential in the number of examples. I mentioned we have a lower bound, which says at least the first order versions of the problems are x time complete, they're x time hard. But the lower bound doesn't rule out a more fine-grained analysis where maybe there are algorithms that are efficient in the number of structures, but maybe inefficient in the sizes and the number of variables. And second, can all of these results and the technique be adapted to handle cases where there's noise? So maybe in the separation problem, some of the labels are corrupted and you're looking for kind of a best fit separator. Okay, so thank you very much for listening. My email's on the bottom there. I'd be happy to answer questions over email, and thanks.